So welcome everyone to this presentation about the Oracle Globally Distributed Database, which is the new name we have now for sharding. I'm Francois Pons. I report into the database product management, and I'm happy to spend an hour or so with you around this exciting topic. As usual, this is the safe harbor statement, which reminds you that this is for your information only. It should not be considered legally binding. So my agenda is first to try to explain what is a distributed database and in which cases it is interesting to use such an architecture. We then look at the various distribution methods and replication methods so that we are highly available. And we look at the different deployment architectures that are available. One interesting case is when you use an autonomous database as a shard candidate. We look into that. And I'll spend some time on one of the recent features, part of the 23 release of the database, which introduces a new way to replicate data. It's called the Raft replication. And it's interesting because it's very easy to use. It's very transparent to the application, and it doesn't demand to configure any data guard or any Golden Gate replication that's a little bit demanding more administration. And I'll show you a demo. We will create together a sharded database using Raft replication so that you can get a better understanding. So I'll try to spend half an hour on my presentation and half an hour on my demo. So let's get started by defining what's a distributed database. So a distributed database is a database that is implemented as a collection of physical databases. So you have one logical database, but technically you have a potentially large number of physical databases. And data is distributed across all these physical databases that we call shards. Of course, the physical distribution is transparent to the application. It's an architecture that still creates one logical database. So we have supported such an architecture since Oracle 12, actually, in 2017, when we introduced sharding. And today we have changed the name into globally distributed database, but sharding and globally distributed database are synonymous. It's essentially the same thing. And we have a lot of large customers using global applications who use this sharding architecture. But because perhaps we have a lot of new features that make it even easier in the recent versions of the database, like 19c and even 23, I think this architecture is going to become more popular over time. So there are essentially two use cases for distributing your database over several physical databases. The first one on the left part of my screen is to achieve a very high level of scalability. If your application allows to run transactions on these different shards in parallel with little to no interaction between the shards, you can reach a very high level of scalability because it's essentially a shared nothing architecture. The shards are independent from each other, and once again, if your application allows this architecture, you can run an application over a potentially very large number of such shards, maybe 100 of them. And so you can achieve a very high level of scalability. The other use case is when you need to implement what is known as data sovereignty. You know that more and more there are regulations that demand that data is managed and saved regionally. Like, for instance, in India, you may have an application that has to keep the data in India. And so sometimes even a global application should keep Indian data in India and European data stored within the European Union. And so if you want to abide by these regulations, maybe breaking a large database into those smaller units that you can keep in different geographies helps to implement data sovereignty. It's another big use case. So essentially, you have one logical database, as we said. So you need an application that's able to route a transaction to a certain shard, and then the transaction should find in that local shard everything it needs to be processed. So that, for instance, if you look at my picture on the right-hand side, red transactions happen on the shard 1, as blue transactions are processed on shard 3 in parallel, with little to no interaction between shard 1 and shard 3. And this allows you to spread your load across a large number of shards. Potentially, you can implement queries in parallel across a very large number of shards. Of course, you can route most transactions so that they are executed on only one shard, but still a few transactions may demand to be executed on multiple shards. So we have this possibility to get a specific connection that allows to connect to a query coordinator, and that query coordinator can split a SQL statement so that it is executed on several shards, and then the results is aggregated to be sent back to the application. So, but essentially, this should happen only by exception. Most of the transactions should be routed to just one shard so that your system remains scalable. But of course, you want also to add some replication. You know, essentially, this shared nothing architecture is also robust in itself, because should you lose one shard, all the other ones should not be impacted. So if you have 10 shards, you lose one, 90% is still alive. But still, you don't want to lose even 10% of your data. So to avoid that loss, you should replicate each shard or even the data within shards. And there are several methods to allow this replication to make your system not only distributed, but also highly available by replication. And so we have several ways to do that. And not only can we achieve this highly available environment, but we can also make a sharded database very elastic, if you will, because data can be redistributed across shards automatically should you decide to add a new shard to an existing sharded database. So the system allows you to add and remove shards and would automatically redistribute and replicate as per your infrastructure your data. It is very important to not confuse and to distinguish correctly sharding from clustering. We've supported clustering since Oracle 9 for a much longer time with what infrastructure we call RAC, Real Application Clusters. And we've supported sharding since Oracle 12, as I said. Both architectures scale out database processing across multiple computers, but in different ways. You see, in RAC, you have essentially one database that is accessed through multiple runtimes. With sharding, you have one logical database, but it is implemented as a large number of physical databases. If you look at RAC, the good thing it is that you can run any application on such an infrastructure. This is why we chose the name RAC, RAC means real application. And by real application, we meant that you can take any application, whatever the schema may look like, and that application should benefit from this architecture. It should be able to run with no problems and no modifications. However, for such an architecture, a multi-runtime architecture for the single database to be efficient, you need the different computers to be very tightly integrated with each other. So typically, they share an infrastructure. It's a shared everything infrastructure. In particular, they share the network, and usually it is a very good network with a high bandwidth and low latency, potentially a RDMA network with a remote direct memory access and very microsecond latency, very small latency. However, this is only achievable when there are not so many nodes, maybe less than 10. And they are very tightly integrated close to each other. So that's good, but doesn't allow you to run over 100 nodes. However, the good thing, once again, is that there are no constraints on the schema. Distributed databases, sharded databases, however, they can be using hundreds of nodes, but at the expense of having a constraint on the schema. You must have a schema that allows to distribute the data by something. So the schema must be somewhat hierarchical. You must distribute the schema with a certain rule. And so not every application is able to happily run on such an architecture. It must be, once again, using a hierarchical schema so that most transactions, once routed to the right shard, can find everything they need on that local shard to be processed without interaction with the rest of the shards. So the good news, however, is that both architectures, sharding and clustering, can be combined, because in sharding, a shard is essentially a physical database, and it could be implemented on a cluster. This is actually one way to make it more robust, because a rack cluster is essentially very redundant. Everything is redundant. So it makes your database more highly available in itself without having to replicate data. So you can choose what architecture between clustering and sharding fits better your needs, or you can even combine both using clusters for shards. Now let's look at the various distribution methods. You know, the key is to find a way to distribute your data across shards. You need to distribute by something. It could be by value or by a range of value or something. You could distribute your data by country code, for instance, or by region, or most often you would just like something that is automatically spreading evenly your data across multiple shards for scalability. And for that, we have a system managed data distribution that would use your sharding key to be hashed by hashing it to evenly distribute your data, the whole schema, across a certain number of shards. And I highlight in my slide customer ID here, because in my demo, I'll be using a data model where customers enter orders, and these orders have line items. And we use on the top of the hierarchy, we use the customer ID as a sharding key. And I'll show you how we can distribute the data evenly across 3 shards by sharding them through this customer ID. And Oracle does a very good job at making an even distribution in that case. Also, you can do a 2-level sharding model. You can do what we call composite data distribution, where, for instance, you might want to first distribute by country or by region, for instance, to abide to sovereignty regulations. And inside a region like EMEA, Europe, you can spread across a certain number of shards evenly by another criteria, like customer ID. So we allow very complex architectures where you shard first by country, then by customer ID, for instance. Now, let's look at the way to duplicate the data so that your system remains highly available, even if there would be an outage or a potential problem on one shard. So first of all, I have to tell you that not only do we distribute data, but some small tables that are used in joins, like price lists or a table of products, they are duplicated to be available on every shard. So we have two kinds of tables, basically. We have the tables that are distributed and the tables that are replicated. And obviously, when a table is replicated, you can maintain it from the application with simple DML statements. You don't do it several times, one time on every shard. You maintain it centrally, and it is synchronously made available on every shard. So you have duplicated tables. But globally, we also want to replicate data across through this infrastructure. So let's look at the methods for doing that. So historically, we have been doing essentially data guard and golden gate at the shard level to provide a high availability on the shard level. And data guard is still maybe the best practice because data guard is extremely fast. It is very complete. It is quite simple to operate. It's a little bit more complex in the beginning because you need to describe this infrastructure, but it's still one of the best practices. Golden Gate has been available for sharded databases from the beginning and through 19C. We started to deprecate it in 21C, meaning, please, this may not be the best solution in the future. Don't use Golden Gate to replicate your shards if you can. We started to say that in 21C, and we disupport that in 23 because now we have developed this Raft replication that is more like an industry standard. And above all, it is something that is easier to configure and to administer. So today, what you can do is either you use a cluster for the shard and you trust that the cluster is robust enough so that you don't even need to replicate anything, or you replicate the shard by data guard, or you decide within a shard group to use this new Raft replication process that I will describe a little later, and I will demo also at the end. So let's look briefly at the deployment architectures. Once again, there is a wealth of possibilities. One possibility is to break down a large database over a very large number of simple shards running on commodity servers with just, let's say, Linux boxes. And a shard is just one Oracle database. It doesn't need to have any specific options, technically at least. An enterprise edition database can be a good shard candidate, and you can install it yourself. There are ways sometimes, depending on how you describe your topology, there are ways so that this system is provisioned from the sharded topology, but usually you can just install yourself by DBCA a shard candidate and tell the sharded database, okay, please use that shard. At the other end of the market, if I can say so, you can have huge applications using the best hardware that Oracle can provide, exadata machines on fault-tolerant scalable clusters hosted on Exadata machines. So you can have an application that runs worldwide and that uses shards that are using Exadata machines. And each one is a very high performance cluster. So you can do everything in between, of course, and you can also leverage clouds to to provision your shard candidates. And that doesn't have to be only the Oracle Cloud. You can have a sharded database that has some shards hosted on the Oracle Cloud as well as on foreign clouds. And you can have a mix also of shards that are on premises and shards that are hosted in the cloud. So it's really very flexible. There are few constraints on where your shards should be. So let's look at one particular model where you want to leverage the performance and ease of use of an autonomous database to become a shard. And we call that, in that case, the globally distributed autonomous database, because the shard is an autonomous database. So this is something we are still developing. Today, it's only available in a limited number of cases, but it is worth mentioning for sure. So the idea is, as I told you, to combine the power of an autonomous database with this architecture. And of course, one of the problems that you want to address when you create a sharded database is you need to provision a lot of things, right? You need to provision the databases that are shard candidates. And as I told you, you can do that manually wherever you want. But if you want to create really a lot of them and on a complex infrastructure, such as Exadata, you might want to have some assistance. So with this architecture, not only are we offering to use autonomous databases, but we are offering also a wizard to help you in the provisioning phase of the system. And so it is good to use for the large applications that want to potentially replicate first by country or by region, and inside the region across a large number of shards for scalability and for also availability. So typically, in this case, you want to use a very high-end infrastructure for your system. Today, we offer globally distributed autonomous database only in 19C. So it's one limitation, because already we support 23 as a platform service, but not yet as a globally distributed autonomous database. And the autonomous database has to be on dedicated infrastructure. We are thinking to providing this sort of infrastructure also on shared infrastructure, but it's not yet available. Today, it is 19C and with autonomous database on dedicated infrastructure. However, what we have is a wizard. If you look at the OCI console, we have even a graphical way of picking a few regions to describe where you want to add your shards. And here we see, for instance, the provisioning of a sharded database that is implemented over autonomous databases on dedicated infrastructure. And we see we have one shard in the US, in Ashburn, and this is being given 8 eCPUs. And we want to make that shard, which is in the US in Ashburn, more highly available by enabling DataGuard, so that it gets replicated within this region to Phoenix by DataGuard, by autonomous DataGuard. And that application has also an Indian shard, which is in Mumbai, in Bombay, and this is replicated in Hyderabad. Okay, so you can describe by means of this little wizard the whole infrastructure, and in the end you click on a button to deploy it, and it's deployed on your behalf. And we want to make that available perhaps tomorrow, even on different lighter infrastructure. But today, this is what we have. Now, let's look at the Raft replication. It is, as I said, a new way that implements a very industry standard protocol known as Raft to replicate data. And in that case, you replicate data within a shard group of a certain number of shards. Your data, not only is it distributed, but it is put into replication units. And we use what is called in Raft vocabulary, a replication factor of 3, which means that each replication unit gets 2 copies. One is, so 3 in total, if you will. One replication unit master copy is called the leader, and it gets 2 copies that are called followers. And of course, the 3 copies are distributed across 3 different shards. So potentially, you need to have at least 3 shards if you want to use that infrastructure. That's number 1. Number 2, if you have 10 shards, each replication unit will use 3 of these 10 shards, but not the same ones. However, for each replication unit, there is one master copy where normally updates are processed, and then these updates are synchronously propagated to the other replicas. So it's an active-active symmetric configuration. The main advantage is that once it is described and it's only a few metadata instructions, it is very transparent. You don't have to worry about how it is implemented. It works very well, and it works completely automatically. And you have no golden gate or no data guard to configure or administer yourself. That's the main advantage. So typically, that works well if you have also shards that are reasonably well integrated with each other, because you have some kind of communication at the shard level, but it's only for each replication unit. Once again, if you have 10 shards, each replication unit will be using 3 of the 10 shards. Okay, so you need to have reasonably good latency if you want this model to work well. It's not necessary to use it. You can prefer to not replicate, perhaps because your shards are using clusters, or to replicate each shard by data guard. In that case, there is really no interaction between shards, across shards. So let me show you a little demo, and before I will stop recording, and then I will record my demo separately.